Welcome to Night Cosmos Sleep, a place where we slowly wander through the strange stories of the universe. On today's journey, we will travel to a world where morning has never appeared. About 20 light-years from Earth, there is a world drifting freely through the Milky Way without orbiting any star. Because it has no sun of its own to illuminate its atmosphere, sunrise and sunset as we know them do not exist there. This world is called SIMP 0136. Most of the planets known to humanity are connected to a star. Earth and Jupiter both orbit the Sun, while many exoplanets are discovered through the effects they have on their host stars. SIMP 0136, by contrast, moves through space alone, carrying its own atmosphere across the vastness between the stars. From Earth, this object appears only as a faint point of infrared light. Behind that tiny glow lies a giant gaseous world, close to Jupiter in size but many times more massive. It has no clearly defined solid surface where a person could stand. Instead, it is made of layers of atmosphere that grow increasingly dense with depth. SIMP 0136 rotates extremely quickly, completing one full turn in about 2.4 hours. This rotation does not create day and night as it does on Earth, but it still causes different regions of the atmosphere to face us and then disappear from view. As that happens, the object's infrared brightness changes as well. The James Webb Space Telescope observed these subtle variations continuously for many hours. It cannot directly see each individual cloud, but it can detect that the atmosphere of SIMP 0136 is neither uniform nor still. Some form of weather is unfolding there, even though this world receives no light from a nearby star. The central question, then, is not only about the darkness of SIMP 0136, but also about how it continues to remain active. What keeps its atmosphere in motion? And how can we study weather on an object that appears only as a distant point of light, 20 light-years away? To begin searching for an answer, we first need to understand what kind of world SIMP 0136 truly is, and why scientists still cannot place it entirely within any familiar category. To understand why SIMP 0136 is so unusual, it helps to begin with the more familiar worlds around us. Earth moves around the Sun, completing one orbit in about a year. Jupiter follows its own path around that same star. On every planet, light, temperature, and the rhythm of the seasons are shaped by the distance from the source of light at the center. The same is true for most planets discovered beyond our solar system. They are often detected when they pass in front of their host stars, causing the star's light to dim briefly, or when their gravity makes those stars wobble ever so slightly. In such cases, the star not only provides light, but also helps astronomers determine where the planet is. SIMP 0136, however, appears without any nearby star to guide us. Observations have found no central source of light around which it is orbiting. It moves independently through the Milky Way, drifting through space alongside billions of stars while belonging to the orbit of none that we know. For this reason, SIMP 0136 is often described as an isolated planetary mass object. The wording is deliberately cautious. It tells us that the object has a mass similar to that of giant gaseous planets and exists on its own, without assuming that it truly formed as a planet. That distinction matters because, in astronomy, a world is not defined only by its size or mass. The way it came into existence can also shape the name we give it. A planet like Jupiter forms within a disk of gas and dust surrounding a young star. Tiny particles collide, join together, and gradually build a larger core. Once that core becomes massive enough, its gravity begins to capture enormous amounts of gas from the surrounding disk. Over millions of years, a gas giant can emerge. Objects like SIMP 0136, however, may also be born through a different process. Instead of forming within a disk around a star, a region of gas inside a molecular cloud may collapse under its own gravity. This is closer to the way a star is born, except that the original clump of matter is too small to become an ordinary star. From these two possible pathways, scientists have proposed two broad histories for SIMP 0136. In the first, it was once a planet belonging to a star system. During their early stages, planetary systems are often far less stable than they are today. Young worlds can pass close to one another, exchange energy, and alter each other's orbits. A planet may be pushed into a more distant orbit, sent falling toward its star, or thrown out of the system entirely. If that happened to SIMP 0136, it may have begun its life beneath the light of a star before a gravitational encounter carried it into interstellar space. Since then, it has continued moving through the Milky Way without orbiting the place where it was born. The second possibility is that SIMP 0136 never belonged to a planetary system at all. It may have formed directly from a collapsing cloud of gas, much like a very small star. In that case, its isolation would not be the result of being cast away. It would have existed alone from the beginning. These two histories can produce objects that look remarkably similar today. A gas giant expelled from its star system and an object formed directly from a cloud of gas may have nearly the same mass, may orbit no star, and may both shine mainly in infrared light. After hundreds of millions of years, clear traces of where they were born can be extremely difficult to preserve. That is why scientists still cannot say with certainty whether SIMP 0136 is a wandering planet that was once ejected or a very low-mass brown dwarf. The data suggests that it belongs to a group of young objects moving together through space known as the Carina Near-Moving Group. By estimating the group's age at around 200 million years, researchers have been able to place the mass of SIMP 0136 at close to 13 times that of Jupiter. That figure brings it directly into the boundary region commonly used to distinguish giant planets from brown dwarfs. The dividing line is often placed near 13 Jupiter masses, where an object may begin burning a heavy form of hydrogen, called deuterium, for a limited period of time. But this is not an absolute boundary. Nature does not separate worlds into clear categories using a single number. An object's exact mass, chemical composition, and formation conditions can all shift that threshold. Even knowing that an object once burned some deuterium is not enough to reveal the full story of how it formed. SIMP 0136 therefore occupies a gray area between two names. It has the mass of a giant, gaseous world, yet it may have formed in a way more closely related to a small star. Calling it a wandering planet could be accurate if it was born within a planetary system. Calling it a low-mass brown dwarf could also fit if it formed directly from gas and dust. For now, the safest description remains an isolated planetary mass object. This uncertainty does not make SIMP 0136 any less interesting. On the contrary, it makes the object a natural bridge between planets and brown dwarfs. Its atmosphere shares many qualities with those of giant planets, while its origin may involve processes that more commonly create stars. Its relative closeness also makes SIMP 0136 well-suited for observation. 20 light-years is still an enormous distance for human beings, but within the Milky Way, it is considered part of the solar system's neighborhood. The light reaching us today left this object about 20 years ago, rather than traveling across hundreds or thousands of light-years. The isolation of SIMP 0136 offers another important advantage. When astronomers study an ordinary exoplanet, its host star is usually far brighter than the planet itself. The faint signal from the planet's atmosphere can be overwhelmed by the nearby starlight, much like trying to see a tiny flame beside a powerful searchlight. With SIMP 0136, that searchlight does not exist. Telescopes can collect the infrared radiation emitted directly by the object itself without having to separate it from the light of a host star. It is also one of the brightest objects of its kind in the northern sky, allowing instruments to track subtle changes in its light with greater precision. This makes SIMP 0136 a natural laboratory for studying giant gaseous worlds. What we learn from it may help us better understand the atmospheres of exoplanets that orbit close to stars where the planet's own light is far more difficult to observe. Even so, the question of its origin remains open. SIMP 0136 may once have formed within a crowded planetary system before being thrown outward by a gravitational encounter. Or it may never have known a nearby host star, having formed alone from the beginning out of a cold cloud of gas in space. Until more evidence becomes available, both possibilities must remain. SIMP 0136 is therefore more than a world drifting freely through space. It is also a reminder that the boundary between planets and stars can sometimes be far less distinct than the names we use to describe them. Whether it is called a rogue planet, a planetary mass object, or a very small brown dwarf, SIMP 0136 still carries an enormous atmosphere through its solitary journey. Drifting through space with no nearby sun, this world continues to release energy that our telescopes can detect. That energy does not come from any external light. It has been stored within SIMP 0136 since the object first formed and is still slowly escaping after nearly 200 million years. This internal heat will lead us into the next part of the story, where darkness does not necessarily mean cold. SIMP 0136 drifts through space without a nearby star to warm it, but that does not make it a cold and motionless world. On the contrary, its atmosphere remains hundreds of degrees Celsius and continuously releases energy in the infrared. This heat does not come from outside. It has been stored within SIMP 0136 since the object formed about 200 million years ago. At that time, gas and matter within a region of space began gathering under the influence of gravity. As more material was drawn into a smaller volume, the pressure inside increased, and some of the gravitational energy was converted into heat. The young object gradually became hotter, denser, and more structurally stable. This is a process that commonly occurs when stars, brown dwarfs, and giant gaseous worlds begin to form. When a body contains enough mass, the temperature and pressure at its center can rise high enough to sustain hydrogen fusion. This is how a star, like the Sun, generates energy through most of its life. SIMP 0136 was not massive enough to reach that stage. It does not have a core that continuously converts hydrogen into helium, nor does it shine like an ordinary star. Yet, failing to become a star does not mean that all the energy from its formation disappeared. An enormous amount of heat remained trapped within its deeper layers, where matter is compressed under intense pressure. Since its birth, SIMP 0136 has been slowly releasing that heat over hundreds of millions of years. This process can be imagined through a stone that has just been heated in a fire. Once removed from the flames, the stone does not immediately return to its original temperature. It continues to radiate heat for some time. SIMP 0136 is not a solid rock, and its internal structure is far more complex, but the comparison helps illustrate how an object can continue releasing energy even without a nearby source of heat. The greatest difference is one of scale. A stone may cool within a few hours, while a world with nearly 13 times the mass of Jupiter requires far longer. The deep layers of gas inside SIMP 0136 are strongly compressed, preventing heat from escaping quickly. Energy must travel through many layers of matter before reaching the upper atmosphere and finally leaving the object as radiation. SIMP 0136 is also continuing to contract very slowly under the force of its own gravity. As matter is compressed deeper inside, some gravitational energy is once again converted into heat. Its energy source is therefore not only the heat left over from formation, but also the prolonged contraction of a giant gaseous object that is gradually cooling. The way SIMP 0136 is heated is very different from the way Earth is heated. Most of the energy that controls our planet's climate and weather comes from the sunday. Sunlight warms the land and oceans, and that heat is then transferred into the atmosphere. Differences between warmer and cooler regions create winds, clouds, ocean currents, and many other familiar weather patterns. On SIMP 0136, energy moves mainly in the opposite direction. Heat from the deeper layers rises upward, warming the atmosphere from within. Hot gas tends to rise, while cooler regions sink. These currents continually carry energy and material between different depths, preventing the atmosphere from ever becoming completely still. Talking about the temperature of SIMP 0136 is also different from measuring temperature on Earth. The object has no clearly defined solid surface where a thermometer could be placed. The deeper we go, the denser the gas becomes, the greater the pressure grows, and the boundary between the atmosphere and the interior becomes increasingly difficult to define. For this reason, the temperatures astronomers discuss are usually inferred from the atmospheric layers where radiation can escape and reach a telescope. Estimates suggest that the observable layers of SIMP 0136's atmosphere are hotter than 800 degrees Celsius. Some models give even higher values, depending on the depth and wavelength being studied. The layers deeper inside may be much hotter, but light from those regions must pass through enormous amounts of gas and cloud before it can escape. At such temperatures, many materials familiar on Earth may exist in entirely different states. Silicates, the group of minerals commonly found in rocks and sand, can become vapor in regions hot enough. When gases carrying these materials rise into cooler layers, the compounds may condense into tiny particles and form layers of mineral clouds. Iron may take part in a similar cycle within deeper regions of the atmosphere. On Earth, iron usually exists in rocks or as solid metal. Under the hot, high-pressure conditions of SIMP 0136, it may become part of cloud layers beneath the silicate clouds. These formations are nothing like the white water clouds in Earth's sky. Instead, they are layers of mineral particles suspended within a hot, dense environment that is constantly in motion. Cloud formation depends on the temperature and pressure at each depth. As hot gas rises from below, it gradually cools, creating conditions in which certain materials can condense. If cloud particles are carried downward into hotter regions, they may evaporate again. This process repeats continuously, producing a weather cycle based on rock and metal rather than water. The internal heat, therefore, does more than make SIMP 0136 glow in infrared light. It also sustains convective currents, transports material between atmospheric layers, and creates the conditions needed for different kinds of clouds to form. The darkness surrounding this world does not bring its activity to a halt, because the energy driving its atmosphere already exists deep within it. Most of that energy escapes as infrared radiation, a form of light invisible to the human eye. Invisible light, SIMP 0136 would appear extremely faint compared with a star. But to a telescope designed to detect infrared radiation, it becomes much clearer because its entire hot atmosphere is continuously radiating heat. This is why the James Webb Space Telescope can study SIMP 0136 even without light from a host star reflecting off its atmosphere. Webb collects the radiation emitted directly by the object itself. As that light travels through the atmospheric layers, some wavelengths are absorbed more strongly by molecules and clouds, while others escape more easily. These differences preserve information about temperature, chemical composition, and the depth from which the light began its journey outward. SIMP 0136 is still relatively young compared with many objects in the Milky Way. Its estimated age of about 200 million years is only a small fraction of the Sun's age. That youth allows it to retain more heat and shine more brightly in the infrared. As it continues to age, the object will gradually cool and become fainter, while the types of clouds that can form in its atmosphere will also change with the temperature. For now, the remaining heat is still sufficient to sustain a dynamic atmosphere. Gas currents continue to move, material is constantly carried upward and drawn back down, and cloud layers may form and disappear as conditions change. SIMP 0136, therefore, shows that a world does not need sunlight to have weather, as long as enough energy remains inside to keep its atmosphere in motion. That internal heat explains why this world is still hot, but it does not yet reveal how different regions of the atmosphere are arranged. Some areas may be warmer, some may contain thicker clouds, while others may expose light rising from deeper layers. To detect those differences, astronomers must observe SIMP 0136 as it rotates, bringing each region into view in turn. With one rotation lasting only about 2.4 hours, this world does not make observers wait very long. Each turn reveals another part of the atmosphere, allowing tiny changes in brightness to begin tracing the shape of the weather unfolding within. Heat from within keeps the atmosphere of SIMP 136 inches motion, but it is the object's extremely rapid rotation that allows astronomers to detect those movements from 20 light-years away. Earth takes nearly 24 hours to complete one rotation, while Jupiter takes about 10. On SIMP 0136, the entire cycle is compressed into roughly 2 hours and 24 minutes. This interval can sometimes be described as a rotational day, though it does not mean the same thing as a day on Earth. Sunlight does not sweep across each region in turn to create morning, noon, and sunset. As SIMP 0136 spins on its axis, a region of the atmosphere simply rotates into view, moves across the side facing the observer, and gradually disappears around the far side. About 2.4 hours later, that same region returns to nearly its original position. This is an exceptionally fast rotation for a world close to Jupiter in size. In roughly the time it takes to watch an American football game from beginning to end, nearly every region of SIMP 0136's atmosphere has faced Earth in turn. Because of this, a telescope observing for only a few hours can record more than one complete rotation. From our distance, SIMP 0136 is still far too small to appear as a clearly defined sphere. Telescopes cannot resolve individual cloud bands, hot regions, or separate atmospheric currents. The entire world fits within a single point of infrared light. Yet that point does not remain constant. Its brightness rises and falls in a rhythm close to the object's rotation period. If the atmosphere had the same temperature and cloud thickness everywhere, rotation would produce very little change. No matter which region faced Earth, the amount of radiation we received would remain nearly the same. Observations instead show that some areas emit more infrared light, while others are slightly dimmer. As these regions rotate in and out of view, the total brightness of SIMP 0136 changes with them. A relatively bright region begins to appear along the edge of the world, then occupies a larger portion of the atmosphere facing us. The amount of radiation collected by the telescope slowly increases. As that region continues around to the far side, the brightness gradually falls, and another area comes into view. Nearly 2.4 hours later, the original pattern returns, creating a measurable rhythm of rising and fading light. These variations are not large enough to make SIMP 0136 look like a lamp being switched on and off. The difference represents only a small fraction of its total brightness. Even so, infrared instruments are sensitive enough to record each change and arrange them over time into a curve. This curve is known as a light curve, and it provides the clearest trace of the object's rotation. A telescope observing Earth from very far away could receive a similar signal. At a great enough distance, our planet would no longer appear with clearly visible continents and oceans, but only as a point of light. When the vast Pacific Ocean rotated into view, the amount of reflected light would differ from when North America appeared. Clouds covering the Midwest, storms moving across the Gulf of Mexico, or the bright, dry surface of the American Southwest could all cause the planet's overall brightness to shift slightly. A distant observer would not see California, the Rocky Mountains, or a cloud system passing over Florida as separate features. They would detect only a point of light growing slightly brighter and dimmer. Yet if they watched long enough, the pattern of variation could still reveal Earth's rotation rate and show that its surface and atmosphere are not uniform everywhere. SIMP 0136 is studied according to the same basic principle. although the light it emits is not mainly reflected from a star. It is infrared radiation produced by internal heat that travels through the atmosphere and escapes into space. A warmer region may emit more radiation. A region covered by thicker clouds may block some of the heat rising from deeper layers, while thinner clouds may allow more energy to escape. Because several factors can change the brightness, the light curve alone does not immediately reveal whether the cause is clouds or temperature. It only confirms that the atmosphere is uneven and that these features are rotating with the world. Even so, this is an important discovery because it makes it possible to measure the rotation of an object with no clearly visible surface. The rotation period of about 2.4 hours was identified through infrared observations made before the James Webb Space Telescope studied SIMP 0136. When the brightness repeatedly rose and fell over nearly the same interval, scientists could connect that rhythm to the object's rotation. Bright and dark regions in the atmosphere acted as markers, much like a large cloud feature can help observers follow the movement of a distant planet. But the light curve of SIMP 0136 does not repeat in exactly the same way every time. Observations made on different nights show that the shape of the curve can change. Sometimes the brightness peak is more pronounced. Sometimes the light fades in a different pattern, and certain smaller features may disappear between observations. If the bright and dark regions were fixed within the atmosphere, each rotation would produce almost the same light curve. The changing shape of the curve shows that these structures evolve over time. Clouds may thicken or begin to clear. Warmer regions may shift, and atmospheric currents may carry features into new positions. This shows that SIMP 0136 does not simply carry a patchy atmosphere rotating steadily around its axis. The patches themselves are constantly evolving. A region visible during one rotation may already have changed by the time it returns less than 2.5 hours later. Weather is unfolding at the same time as the entire world continues to spin. Its rapid rotation makes SIMP 0136 an especially favorable target for observation. If a world takes several days to complete one turn, a telescope must watch for a long time to record every region of its atmosphere. With SIMP 0136, a single night of observation can cover multiple rotations, allowing the same area to be compared each time it comes back into view. During the first rotation, a region of the atmosphere may emit a relatively large amount of radiation. The next time it appears, that same region may be dimmer or arrive earlier than expected. A change in brightness suggests that its temperature or cloud cover has shifted, while a change in timing may indicate that atmospheric currents are carrying the feature around the world at a different speed from the interior below. The atmosphere does not necessarily rotate like a rigid shell fixed to the object. Its currents may move faster or slower, much as weather systems on Earth do not remain over the same longitude. A storm forming off the coast of California may gradually drift inland, while the planet continues to rotate beneath it. Atmospheric structures on SIMP 0136 may move in their own way as well, even though we cannot yet see their shapes directly. The rapid rotation may also strongly influence the way gases move. On a fast-spinning world, atmospheric currents are more likely to stretch from east to west rather than flow directly from warmer regions toward cooler ones. Jupiter reveals this effect through the long cloud bands that circle the planet. SIMP 0136 rotates several times faster than Jupiter, so its atmosphere may be shaped even more strongly by its spin. Even so, a single overall light curve tells us only whether the total amount of radiation is rising or falling. A brighter region could be warmer, covered by thinner clouds, or shaped by both effects at once. When all the light is combined into one measurement, these different causes are extremely difficult to separate. The James Webb Space Telescope changed the way this signal could be read by treating infrared light not as one single block, but as many separate wavelengths. It divided the light into different groups and followed each one throughout the rotation. Some wavelengths grew brighter when a particular atmospheric region came into view, while others became dimmer or remained almost unchanged. These differences show that not every wavelength comes from the same place. Some forms of light escape from deeper layers, where the pressure is greater and hot clouds exist. Other wavelengths carry information from higher regions, where temperature, atmospheric chemistry, and magnetic activity may leave their own distinct signatures. The 2-4-hour rotation therefore becomes a natural scan across the entire atmosphere. Each region moves into view in turn, while light at different wavelengths helps distinguish what is happening at different depths. From a single tiny point of light, SIMP 0136 begins to reveal both the changes unfolding around its rotation and the structure extending from its upper atmosphere into the deeper layers below. The rhythm of brightening and dimming has already shown that this world has weather. The infrared colors separated by James Webb will now carry us deeper, into cloud layers that may be made of materials very different from the water clouds found on Earth. The rapid rotation of SIMP 0136 allows astronomers to see that its brightness is constantly changing. But those changes do not come from a single atmospheric layer. Light at each wavelength responds in a different way, almost as though it is emerging from a different depth. When these signals are combined, the atmosphere of this world begins to appear not as one simple cloud layer, but as a complex system of many layers moving together. In the upper atmosphere, the gas is relatively thin and the pressure is much lower than it is below. Heat rising from the deep interior of SIMP 0136 must travel a long way before reaching these heights. Warmer or cooler regions at this altitude can cause certain infrared wavelengths to vary noticeably, even when the temperature differences themselves are not especially large. This is also where the atmosphere may be more strongly influenced by the magnetic field. Charged particles and processes occurring at high altitudes can add energy to the gas, causing temperatures in some regions to differ from what would otherwise be expected. Webb cannot see these areas as separate bright patches, but changes in the light suggest that the uppermost atmosphere is not completely uniform. Deeper down, the gas becomes denser, and the pressure steadily increases. Temperatures here remain high enough to create a kind of weather unlike anything familiar on Earth. On our planet, clouds usually begin with water. Water vapor rises, cools, and condenses into tiny droplets or ice crystals. On SIMP 0136, water is not the main material forming the cloud layers Webb is probing. The atmosphere is so hot that substances found in rocks and sand on Earth can become vapor, then condense into tiny particles when they reach a cooler layer of gas. One of those materials is silicate. Silicates are a common group of minerals found in rocks, desert sand, and the crusts of many planets. On Earth, they usually remain beneath our feet. In the hot atmosphere of SIMP 0136, they may take part in an entirely different cycle. Hot gas rising from deeper layers carries material upward. When it reaches a region with the right temperature, silicate vapor can condense into extremely small particles. These particles gather into a layer of mineral clouds suspended in the atmosphere by convection and gravity. These clouds would not resemble the white formations that drift across Earth's blue sky. They may form thick, hazy, heated layers stretching through an atmosphere with no solid surface below. Mineral particles are constantly carried along by atmospheric currents, sinking downward or evaporating again when they enter hotter regions. The pressure in the region where silicate clouds may exist is close to Earth's atmospheric pressure at sea level. This comparison only helps locate the depth within the model. It does not mean that conditions there resemble the atmosphere around us. The temperature, chemical composition, and nature of the clouds are entirely different. Going deeper, the pressure rises several times over. The gas becomes more tightly compressed, the temperature increases, and light from these regions has greater difficulty escaping. Some infrared wavelengths can still carry information from these depths to the telescope, allowing scientists to infer that beneath the silicate clouds there may be another cloud layer containing iron. On Earth, iron brings to mind metal bars, railroad tracks, steel bridges, or ore buried deep underground. Inside SIMP 0136, temperature and pressure may draw iron into an atmospheric cycle. Where conditions are hot enough, iron can exist as vapor. When the gas moves into a cooler region, it may condense into droplets or tiny particles, forming a cloud layer deeper below. These may not be separate clouds, with clearly defined edges. More likely, they form a thick mineral layer mixed with hot gas and constantly reshaped by atmospheric motion. Some regions may contain more particles, while others may be thinner and allow more heat from the interior to escape. The differences between these cloud layers help explain why the brightness of SIMP 0136 does not vary in the same way at every wavelength. Light emerging from deeper layers must pass through more gas and cloud. If a region of iron or silicate cloud becomes thicker, less radiation from below may escape. Where the cloud layer is thinner, heat from the deep interior can pass through more easily, making that area appear brighter in certain infrared bands. The atmosphere can be imagined as a very tall building, except that instead of being separated by solid floors, every layer blends into the next and remains in constant motion. The uppermost regions reveal more about temperature variations and the influence of magnetic activity. Below them lies the region that may contain silicate clouds. Deeper still are dense, heated layers where iron particles may condense. Webb does not see through the entire building in a single observation. Each group of wavelengths opens a window into a particular range of depths. Some wavelengths emerge mainly from the upper atmosphere, while others can carry information from much deeper regions. In the short infrared range, from about 0.9 to 1.4 micrometers, the light can probe layers at pressures near 10 bars. This is a deep region where models suggest iron-bearing clouds may exist. Wavelengths from about 1.4 to 2.3 micrometers carry more information from the region near 1 bar, where silicate clouds may play an important role. Light around 3.3 to 3.6 micrometers is more sensitive to the upper layers, near a pressure of 0.1 bars, where temperature variations become more apparent. These numbers are not rigid boundaries dividing the atmosphere into 3 separate layers. Light always travels through a range of depths, and cloud layers may overlap. The numbers simply help scientists identify which region each group of wavelengths is most sensitive to. When one region of the atmosphere rotates into Webb's view, light from the deeper layers may increase while the signal from higher altitudes remains almost unchanged. At another point, the wavelengths sensitive to temperatures in the upper atmosphere may vary much more strongly. These differences show that the atmosphere does not behave as a single, unified body. One region may have thinner clouds at depth while its upper atmospheric temperature remains similar to that of the surrounding areas. Another may show little change in cloud cover, but be warmer higher up. As the entire world rotates, each structure appears in different groups of wavelengths in turn. This is how spectral data gradually become a picture with depth. Webb cannot directly photograph clouds of iron or silicate. The telescope only collects light and separates it into many narrow bands. Scientists then compare those bands with atmospheric models to find the structure that best matches the observed signal. Each model tests a different arrangement: how temperature changes with altitude, how thick the cloud layers are, how large the particles may be, and which molecules are absorbing the light. When a model produces a spectrum that closely resembles Webb's data, it becomes a well-supported explanation of what may be happening in the atmosphere. For this reason, saying that SIMP 0136 may contain silicate and iron clouds does not mean that Webb has seen individual mineral particles. These cloud layers are inferred from the way light escapes, is absorbed, and changes throughout the rotation. It is an indirect map built from data rather than from an ordinary photograph. Even so, the idea that materials found in rocks and metals can take part in weather is not especially surprising on extremely hot worlds. Under the right conditions, any substance can move between vapor, liquid, and solid states. Water forms clouds on Earth because the temperatures around us are suited to the water cycle. On SIMP 0136, temperatures are far higher, so only more heat-resistant substances can condense. This also means that the cloud layers will change as SIMP 0136 cools. In the distant future, materials that now remain in vapor form may begin to condense at different altitudes. The present cloud layers may sink deeper or be replaced by entirely new kinds of clouds. At the time we are observing it, the atmosphere is still hot enough to sustain these mineral layers. Heat continuously rises from within, carrying material upward from great depths. As the gas cools, cloud particles form. They may then fall, enter hotter regions, and evaporate before taking part in another cycle. A tiny silicate particle might begin in a region of hot gas below, be carried upward by convection, and condense within a cloud layer. It may drift with the winds for some time, slowly sink, and eventually evaporate after returning to a hotter region. At the same moment, countless other particles are following similar paths, creating an atmosphere that is always changing even without sunlight shining upon it. The extremely rapid rotation may also stretch the cloud layers around the world. Atmospheric currents could form broad bands, swirling regions, or patchy structures extending along lines of longitude. Webb cannot yet determine their exact shapes, but the changing light curve shows that the clouds do not cover the entire atmosphere evenly. Some regions may be thicker and more enclosed, trapping more heat below. Others may resemble relatively clear openings that allow radiation from deeper layers to escape more easily. As these areas rotate into view, the brightness of SIMP 0136 changes. For a long time, this was the main explanation for the object's rhythm of brightening and dimming. Thick and thin clouds were thought to create different bright and dark regions, much as breaks in Earth's cloud cover reveal or conceal the surface below. That explanation is reasonable, but Webb's data do not follow such a simple pattern completely. If clouds were the only cause, many wavelengths would be expected to rise and fall in nearly the same way. Instead, some bands of light vary according to very different rhythms, suggesting that the upper and deeper atmospheric layers do not respond in the same way. Silicate and iron clouds remain important parts of the atmosphere of SIMP 0136. They help explain its overall spectrum and the way heat escapes from within. But when scientists examined each wavelength throughout the full rotation, they realized that clouds alone could not explain the entire story. Hidden among the mineral cloud layers are regions with different temperatures, atmospheric currents that transport energy, and processes that may be connected to the magnetic field. The weather on SIMP 0136 is therefore not simply a matter of where there are more clouds or fewer clouds. It is the result of many atmospheric layers interacting with one another, from deep iron cloud regions below to the thin, energetic layers high above. For a long time, the most reasonable explanation for the changing brightness of SIMP 0136 lay in its cloud layers. When a relatively clear region turned toward us, heat from below could escape more easily, making the world appear slightly brighter in infrared light. When a thicker cloud layer moved across the visible side, some of that heat was blocked and the brightness decreased. This explanation is somewhat similar to what happens on Earth. A region with clearer skies often allows more heat from the land and oceans to escape, while thick clouds can alter the thermal signal. So when astronomers saw SIMP 0136 brighten and fade as it rotated, they had good reason to suspect that areas of thicker and thinner cloud were passing through the telescope's view. But the James Webb Space Telescope did more than measure how bright SIMP 0136 was. It also separated the infrared light into many narrow bands, each carrying information from a different depth within the atmosphere. When these light curves were placed beside one another, they did not all rise and fall in the same rhythm. At times, light from deeper layers grew stronger, while the signal from higher regions remained nearly unchanged. At other moments, one group of wavelengths dimmed, even as neighboring bands stayed steady. If all the variation had been caused by a single cloud layer moving in and out of view, the light curves should have looked more alike. The fact that they followed different rhythms showed that the atmosphere of SIMP 0136 was more complex than a sky divided only into cloudier and clearer regions. Clouds were still present, but alongside them were warmer areas, cooler areas, and atmospheric currents carrying energy upward from deep below. Each layer of the atmosphere responded in its own way, so as the world rotated, the light escaping from different depths changed differently as well. A weather map of the United States usually shows more than just where clouds are located. It may also include layers of color representing temperature, humidity, and air movement. One region may be covered by clouds yet still be warmer than the surrounding area. Another may have clearer skies without necessarily releasing more heat. Only by combining several kinds of information can we understand what is truly happening in the atmosphere. Webb is doing something similar with SIMP 0136, even though the entire world still appears as only a tiny point of light. Some wavelengths reveal more about the deeper cloud layers. Others are more sensitive to temperatures in the upper atmosphere. When those signals do not change together, it means that weather is unfolding at several levels at once. Models suggest that the average temperature of SIMP 0136 changes by only about 5 kelvins over one rotation. Compared with an overall temperature of more than 1200 kelvins, that difference is very small. Yet, on a world nearly as wide as Jupiter, a region only a few degrees warmer than its surroundings can still release enough additional energy for Webb to detect. The difference is somewhat like a large city, appearing clearly in a thermal image at night. The city may be only a few degrees warmer than the neighboring countryside, but from above, it still stands out as a warmer region. On SIMP 0136, Webb is also detecting areas with small temperature differences spread across enormous portions of the atmosphere. These warmer regions do not lie on solid ground, because SIMP 0136 has no clearly defined solid surface. They exist within the atmospheric layers themselves. Heat from the interior rises, carrying warmer masses of gas upward. Elsewhere, cooler gas sinks. These motions create regions with different temperatures, and the world's rapid rotation carries them around the globe. A warmer region may appear in the light curve during one rotation, yet by the time it returns about 2.4 hours later, it may already have changed. It may have cooled slightly, shifted to a new position, or become covered by a thicker cloud layer. This is why the light curve of SIMP 0136 never repeats in exactly the same way. It is a sign that the atmosphere is not a fixed picture, simply turning before the telescope. The structures within it are still growing, fading, and drifting. Clouds change, temperatures shift, and atmospheric currents continue carrying matter from one region to another. Silicate clouds still play an important role. They help explain why certain wavelengths are blocked and why heat from deeper layers escapes more easily in some places than in others. Yet the newer data suggests that clouds may not be the main cause of every variation Webb observes. A cloud layer may cover a broad area without changing very much during a single rotation. Meanwhile, warmer and cooler regions higher in the atmosphere may shift more quickly and produce stronger changes in infrared light. This has gradually led scientists away from a picture made only of clouds and toward an atmosphere where many factors work together to create weather. A rising current of hot gas may make one region brighter. When that gas reaches cooler layers, material within it can begin condensing into clouds. The newly formed cloud layer then traps some of the heat below, causing the surrounding temperature to continue changing. Clouds and heat, therefore, do not act independently. They constantly influence one another. The chemical composition changes along with these motions. The atmosphere of SIMP 0136 contains carbon-bearing molecules such as methane, carbon monoxide, and carbon dioxide. They are not distributed in exactly the same way at every depth, because temperature and pressure are always changing. Gas from deeper layers may be carried upward so quickly that the molecules within it do not have enough time to adjust to the new conditions. A substance formed under high temperature and pressure may continue to exist briefly after rising into a higher region. When these masses of gas rotate through Webb's view, they leave slightly different signatures in the light. This does not mean that Webb has seen individual parcels of gas or produced a clear map of every molecule. The telescope has only detected that some chemical signatures vary with the rotation, showing that the atmosphere is not completely uniform from place to place. Early studies, therefore, describe SIMP 0136 as a world shaped by a combination of patchy clouds, warmer regions, and changes in carbon chemistry. More detailed analyses later continue to show that temperature and activity in the upper atmosphere may play a larger role than scientists once thought. This is not a story in which an old explanation has been completely replaced by a new one. Clouds still exist, and they are still essential to understanding the spectrum of SIMP 0136. The difference is that as the data became clearer, the picture gained more layers. At first, astronomers saw a changing point of light and thought of regions with thicker and thinner clouds. Then Webb revealed that each atmospheric layer was changing in its own way. Clouds are part of the weather, but temperature, convection, chemical composition, and magnetic activity are also contributing. This shift in understanding is much like observing a storm from far away. At first, all that can be seen is one enormous mass of cloud. With the addition of thermal images, wind data, and measurements of humidity, the storm begins to reveal a far more complex structure. The cloud layers are only the most visible part. Within them are moving air, differences in temperature, and the source of energy that keeps the entire system alive. The same is true of SIMP 0136. Clouds made of silicate and iron may be the most striking feature, but they do not tell the whole story. Behind those cloud layers, heat is rising from the interior, atmospheric currents are being stretched by the rapid rotation, and regions differing in temperature by only a few degrees are still enough to change the light we receive. This also reminds astronomers to be cautious when studying distant worlds. A single observation may happen to catch a warmer region just as it turns toward the telescope. Another may take place after that region has rotated out of view or become hidden beneath clouds. Two measurements of the same object can look different simply because the weather has changed. On SIMP 0136, the rapid rotation allows Webb to follow these variations over just a few hours. The telescope watches different atmospheric regions pass through view one after another, then compares their light at many different depths. In this way, a world that appears only as a point of light begins to reveal the rhythm of motion within it. Clouds remain an important part of the atmosphere, but they no longer stand alone at the center of the story. The weather on SIMP 0136 is created by the interaction of clouds, heat, atmospheric currents, and chemistry. Each changes slightly, and together they leave their signatures in the infrared light. In the highest layers, Webb has also detected a region of gas that appears warmer than expected. Heat from the interior can explain much of the atmosphere's motion, but it does not seem sufficient to fully explain what is happening at that altitude. Another source of energy may be entering the atmosphere through SIMP 0136's own powerful magnetic field, and that energy will lead us to a phenomenon familiar on Earth, but appearing in a very different form on this world without a sun: auroras. In the upper layers of SIMP 0136, the temperature does not continue to fall steadily as might normally be expected. A thin layer of gas appears to warm again, as though some source of energy is being delivered directly into the atmosphere from above. The heat remaining inside this world can explain much of the motion in the deeper layers, but it is not enough to tell the full story of this unusually hot region. One possibility receiving close attention from scientists is auroral activity. On Earth, auroras usually appear in regions near the two poles. During winter nights in Alaska, the sky is sometimes covered by bands of light that slowly curve above the horizon. Behind that quiet display lies the motion of charged particles arriving from the sunday. As this stream of particles approaches Earth, the planet's magnetic field guides some of them toward the poles. The particles plunge into the upper atmosphere, collide with atoms and molecules, and transfer energy to them. The atmosphere then releases some of that energy as light and heat. An aurora is therefore more than a luminous display in the sky. It is also a sign that a magnetic field, charged particles, and an atmosphere are exchanging energy. On SIMP 0136, the story begins differently. This world does not orbit a host star, so there is no nearby source of steady stellar wind like the stream of solar particles that continuously passes Earth. If auroral activity is truly occurring there, the energy and charged particles must be arriving through another pathway. The first evidence did not come from the James Webb Space Telescope, but from radio telescopes. These instruments detected powerful bursts of radio emission from SIMP 0136. Signals of this kind are often associated with electrons moving through a strong magnetic field, much like the process that produces auroral radio emission on giant planets. From the radio signal, scientists estimate that the magnetic field in the emitting region of SIMP 0136 may be more than 200 times stronger than Jupiter's. This is a remarkable figure for an object near the boundary between a gas giant and a brown dwarf. Earth generates its magnetic field through the motion of electrically conductive material in its interior. Jupiter also possesses an extremely powerful magnetic engine, sustained by matter under immense pressure deep beneath its cloud layers. SIMP 0136 may be operating through a similar mechanism, but under different internal conditions and at a far greater intensity. That magnetic field surrounds the object like an invisible region of influence. Its field lines stretch outward into space and curve back toward the atmosphere, creating pathways along which charged particles can travel. When electrons are accelerated along these lines and plunge into the upper atmosphere, they can transfer energy into the gas. Webb has not captured a clearly resolved auroral display on SIMP 0136. The world still appears only as a tiny point of light, and the telescope cannot distinguish its polar regions from the rest of the object. Illustrations showing auroras surrounding SIMP 0136 are therefore artistic interpretations, not direct photographs. What Webb records is the temperature and infrared light emitted from different atmospheric layers. When the data are incorporated into models, an unusual feature appears high in the atmosphere. Instead of continuing to cool with altitude, the temperature begins to rise again within a relatively thin region of gas. This phenomenon is known as a temperature inversion. On Earth, an inversion can occur when a layer of air above is warmer than the layer beneath it. On SIMP 0136, the warming appears high in the atmosphere and requires a sufficiently powerful energy source to sustain it. Electrons associated with auroral activity may provide part of that energy. As they enter the atmosphere, their kinetic energy is transferred to gas molecules through repeated collisions. Some of the energy emerges as radiation, while some heats the surrounding atmospheric layer. This process does not need to produce a visible display resembling Earth's auroras for Webb to detect it. As long as enough heat is deposited into the atmosphere, it can alter the infrared radiation and leave a signature in the spectrum. Recent analyses suggest that the upper atmosphere of SIMP 0136 may be significantly warmer than it would be if the temperature simply continued to decline with altitude. An auroral model explains this feature reasonably well, especially because the object is already known to produce strong radio emission and possess an enormous magnetic field. Even so, this interpretation is still based on several pieces of evidence brought together. Radio telescopes reveal magnetic activity and emissions consistent with auroras. Webb shows that a high atmospheric layer is receiving additional heat. When these two kinds of data are considered together, auroral activity becomes a plausible explanation, though not a direct image proving exactly where or how it is occurring. The greater mystery lies in the source of the charged particles. Earth has the Sun, while SIMP 0136 drifts alone. There is no nearby star continuously sending a stream of particles into its magnetic field. Some electrons may come from the environment surrounding SIMP 0136 itself. Its powerful magnetic field and extremely rapid rotation may trap, accelerate, and guide particles toward the atmosphere. Within a large magnetic system, rotational energy can also be transferred to those particles, causing them to move faster before entering the upper atmospheric layers. Another possibility brings to mind Jupiter and its moon Io. Io travels within Jupiter's vast magnetic field. Material surrounding the moon enters the magnetic environment, creating streams of particles and helping sustain auroral activity on the giant planet. This connection shows that a planet does not necessarily have to depend entirely on the solar wind to produce powerful auroras. A moon orbiting within the magnetic field can also play an important role. SIMP 0136 may possess an undiscovered moon or companion. As that object moves through the magnetic field, it could generate electrical currents, supply additional charged particles, or accelerate particles that are already present. The electrons could then travel along the field lines and carry energy into the atmosphere. This is an intriguing possibility, but there is currently no evidence confirming that SIMP 0136 truly has such a moon. From a distance of 20 light-years, a small satellite orbiting close to the object would be extremely difficult to detect. It could be lost within the infrared glow of SIMP 0136 itself, or simply be too faint for current telescopes to separate. For now, an undiscovered moon should therefore be regarded only as a possible explanation. It may help account for the source of the charged particles, but it is not yet a piece of the puzzle that has actually been found. Even without a moon, the magnetic field of SIMP 0136 could still create an extremely dynamic environment. The object completes one rotation in about 2.4 hours, far faster than Jupiter. That rapid spin may carry atmospheric gas and particles trapped within the magnetic field, allowing energy to build up before being released in powerful bursts of activity. The radio emissions may be traces of electrons moving at nearly the speed of light within the magnetic field. From Earth, the signal appears as brief radio pulses, like an invisible lighthouse sweeping through space whenever the emitting region rotates toward us. The rotation of SIMP 0136 may therefore control two rhythms at once. In the deep cloud layers, it brings warmer and cooler regions into Webb's view one after another. Higher in the magnetic environment, the same rotation also causes the source of radio emission to sweep past Earth. One telescope receives infrared light from the atmosphere, while another listens for radio pulses from the magnetic field. These two signals are very different, yet both reveal that SIMP 0136 is not a quiet world, simply cooling in the darkness. Below are layers of silicate and iron clouds, sustained by heat escaping from the interior. Higher up, the gas is shaped by convection and differences in temperature. Farther out, the magnetic field extends into space, guiding charged particles back toward the atmosphere. These layers are connected. Energy released near the poles may heat the upper atmosphere. That heated gas can then affect the way heat is transported and the conditions under which molecules can exist. As the atmosphere rotates, traces of this process may appear in the wavelengths observed by Webb. Auroras on SIMP 0136 may therefore look very different from the displays seen in Alaska. What matters is not the color of the light, but the invisible motion of electrons and the energy they carry. From the space surrounding the object, particles are guided down into the thin upper atmosphere, where they collide with the gas, warm the environment, and alter the radiation escaping into space. Although the shape of the auroras cannot yet be observed directly, the available evidence points toward an atmosphere strongly influenced by the magnetic field. Radio emissions show that electrons are being accelerated. The temperature inversion suggests that the upper atmosphere is receiving additional energy. The powerful magnetic field provides a pathway connecting these two phenomena. Within the darkness, with no nearby sun, SIMP 0136 still produces its own forms of light and heat. The energy does not come from sunrise, but may instead arise from rotation, magnetism, and invisible streams of particles moving through the atmosphere. When electrons transfer energy into the upper layers of gas, they do more than change the temperature. These energetic collisions may also affect molecules, breaking certain bonds and opening new pathways for chemical reactions. In an atmosphere that is always moving, its chemistry cannot remain fixed in a single state. To fully understand the weather on SIMP 0136, we must now explore how molecules are formed, transported, and transformed among its heated atmospheric layers. On this world, the composition of the atmosphere is changing alongside its clouds, temperature, and magnetic field. I have developed this section with a gentle narrative flow, allowing the chemistry to emerge through the movement of the atmosphere rather than as a list of molecules and reactions. When charged particles transfer energy into the upper layers of the atmosphere, they do more than change the temperature. That energy can also affect the molecules already present, breaking certain bonds and creating conditions in which new reactions can occur. On SIMP 0136, weather is therefore not limited to clouds, winds, or warmer and cooler regions. The atmosphere's chemical composition may also change as matter is continually carried from one depth to another. When describing the atmosphere of a distant world, it is easy to imagine a fairly fixed list. A certain amount of methane, a certain amount of carbon monoxide, and a certain amount of carbon dioxide. That description is convenient, but a real atmosphere is not like a container whose contents have been evenly mixed and then left undisturbed. It is an environment in constant motion, where temperature and pressure change with altitude and atmospheric currents continuously transport matter from place to place. On SIMP 0136, the difference between the deep and upper layers is especially pronounced. Below, the gas is more strongly compressed and much hotter. As it rises, the pressure decreases and the temperature changes, allowing the same elements to become part of different molecules. A compound that remains stable deep within the atmosphere may no longer be favored after it is carried upward, while a molecule formed in a cooler region may break apart if it sinks back into hotter layers. This process is somewhat like the circulation inside a pot of water being heated on a stove. The warmer water near the bottom becomes less dense and rises, while cooler water above sinks to replace it. The entire liquid continues to circulate, even though the surface may appear fairly calm from the outside. In the atmosphere of SIMP 0136, this motion unfolds across a world nearly as large as Jupiter, among layers of intensely hot gas under enormous pressure. Gas rising from the deeper atmosphere carries molecules formed under hot, dense conditions. As the current moves upward, the surrounding environment changes, but chemical reactions do not always happen quickly enough for the composition to adjust immediately. Some molecules may continue to exist in places where, under ordinary chemical equilibrium, they should already have transformed into different compounds. This is much like taking a hot dish out of the oven. The surrounding temperature has changed, but the inside does not cool at once. For a time, it still carries the imprint of its earlier conditions. Rising masses of gas inside SIMP 0136 may likewise preserve chemical traces of the depths where their journey began. Because the atmosphere is always moving, its molecules do not reflect only the conditions where they are currently found. They also carry information about the places they have recently passed through. A region high in the atmosphere may still contain carbon monoxide formed in hotter layers far below. Elsewhere, the gas may circulate more slowly, giving reactions enough time to produce greater amounts of methane. As these atmospheric regions rotate into the view of the James Webb Space Telescope, the spectrum changes slightly. Some wavelengths are absorbed more strongly, while others become brighter. These variations are very small, but they suggest that the atmosphere does not have the same composition everywhere or at every altitude. Webb's first observations revealed several light curves that could not be fully explained by clouds or temperature differences alone. If a region appeared darker only because its clouds were thicker, many wavelengths should have changed in nearly the same way. Instead, some bands associated with carbon-bearing molecules followed their own distinct patterns. One possibility is that the amounts of carbon monoxide or carbon dioxide are not exactly the same from one region to another. When an area containing more of one of these molecules rotates into view, its absorption signature becomes more pronounced. As that region disappears around the far side, the signal weakens again. This does not mean that Webb has seen clearly defined patches of carbon dioxide drifting around the world. SIMP 0136 still appears only as a point of light through the telescope. Scientists are inferring chemical differences from the changing light, then testing which atmospheric models can reproduce the signal most closely. Each model begins with a hypothetical atmosphere. The temperature is allowed to change with altitude, cloud layers are placed at suitable depths, and the abundance of each molecule is adjusted. Simulated light from the model is then compared with the data collected by Webb. When one arrangement produces a spectrum close to what was observed, it becomes a more plausible explanation. The initial results suggest that carbon chemistry may vary with the rotation. More detailed analyses have also identified a connection between changing temperatures and the amounts of carbon dioxide and hydrogen sulfide inferred by the models. Other molecules, meanwhile, appear to remain more stable and evenly distributed during the period of observation. Hydrogen sulfide is a sulfur-bearing compound. On Earth, it is often mentioned because of its highly distinctive odor, but on SIMP 0136, the smell is not what matters. Its presence helps scientists trace the role sulfur plays in the chemistry of a hot, dense atmosphere. As the temperature changes, the amount of hydrogen sulfide required by the models to explain the spectrum changes as well. This may indicate that the molecule is distributed unevenly, or it may simply mean that temperature is making its signature in the light appear stronger or weaker. These two possibilities can sometimes be extremely difficult to separate. This is one of the greatest challenges in studying an atmosphere from far away. A changing absorption feature does not necessarily mean that the abundance of a molecule has changed. Temperature, pressure, and clouds can also alter the way the same molecule leaves its mark on the light. Scientists must test many possible explanations before deciding which one fits best. The chemistry of SIMP 0136 therefore cannot yet be written as a complete formula. Webb has shown that the atmosphere is complex and uneven, but identifying exactly where each molecule is located remains beyond the reach of current observations. What we do have are signs that chemical composition, temperature, and atmospheric motion are closely intertwined. A rising current of hot gas may carry large amounts of carbon monoxide from deeper layers. As it moves upward, the gas cools and other reactions become more favorable, but the motion may be too rapid for the transformation to finish. The region continues traveling around the world while carrying a chemical composition that does not entirely match its present altitude. Elsewhere, the gas may move more slowly or may have remained in the upper atmosphere for a longer time. The molecules there have more time to change, producing a slightly different mixture. As these two regions rotate through Webb's view, each leaves its own signature in the spectrum. Clouds also take part in this changing chemistry. When material condenses into particles, certain elements are removed from the gas and incorporated into the cloud layer. If those particles sink, they carry matter back toward deeper regions. When they encounter higher temperatures, they evaporate again and return those elements to the atmosphere. The atmosphere therefore behaves like a continuous transport system. Matter rises in currents of hot gas, moves sideways with the winds, condenses into clouds, and then sinks. Along the way, changing temperature and pressure cause molecules to be continually formed, broken apart, or transformed into different compounds. The 2-4-hour rotation stretches this entire system around the world. Regions with slightly different compositions do not remain fixed, but travel with the atmospheric currents. An area observed by Webb during the first rotation may already have mixed with its surroundings by the time it returns during the next. This is one reason the light curves never repeat exactly. The changes come not only from clouds forming or dissipating, but also from the transport of warmer gas, cooler gas, and different molecules. Each rotation captures a slightly different state of the atmosphere. Magnetic activity in the upper layers may make the picture even more complex. Electrons entering the atmosphere carry energy with them, heating the gas and potentially breaking apart certain molecules. The remaining fragments may then recombine through new reaction pathways. Although the precise role of this process is still being studied, it shows that the atmosphere may be altered not only by energy rising from below, but also by energy arriving from above. SIMP 0136, therefore, has no single atmospheric layer that can represent the entire world. The composition we measure depends on the depth a particular wavelength can probe, which region is facing the telescope, and the state of the weather at the moment of observation. One measurement may be sensitive to hot gas rising from deep below. Another wavelength may reflect a higher atmospheric layer where magnetic activity is supplying additional energy. When these observations are placed side by side, scientists find that the same world can carry several different chemical signatures at once. This is also important for the study of other exoplanets. When a telescope observes a distant world for only a few hours, the spectrum it records may reflect whichever atmospheric region happens to be facing us at that time. It may not fully represent the planet as a whole. SIMP 0136 allows scientists to see this problem clearly because it rotates rapidly and is bright enough in infrared light to be monitored continuously. Changes unfold within a single night of observation, showing that atmospheric composition is not one unchanging number that can be assigned to an entire world. Webb has not created a precise map showing where carbon dioxide or hydrogen sulfide is concentrated, nor has it seen individual masses of gas drifting through the cloud layers. What it can do is record changes in the light with enough precision to reveal that the chemistry is moving along with the weather. From these subtle signals, SIMP 0136 gradually emerges as a world that is constantly mixing itself. Heat from within carries gas upward. Rotation draws atmospheric current around the object. Clouds remove material from the gas and return it when they evaporate, while magnetic activity may warm and alter the upper layers. There is no single formula that describes the atmosphere everywhere and at every moment. What exists instead is a system in constant motion, where chemical composition changes along with temperature, pressure, and the direction of the atmospheric currents. All of this has been discovered on an object so distant that the James Webb Space Telescope cannot resolve even a single individual cloud. SIMP 0136 remains only a tiny point of light, yet within that point are signals from many depths, many regions, and many different moments in time. To understand how scientists transform these minute variations in light into an indirect weather map, we need to look more closely at how Webb collects each spectrum as this world rotates. From thousands of measurements taken one after another, a single point of light begins to reveal the structure of an entire atmosphere. From a distance of 20 light-years, SIMP 0136 does not appear as a world with clearly defined edges. The James Webb Space Telescope cannot see individual cloud bands curling around its atmosphere, nor can it yet identify exactly where the atmosphere is warmer or where more silicate may be present. Through the telescope, the entire object remains confined to a tiny point of infrared light. Even so, that point of light is far from simple. The light from SIMP 0136 passed through many atmospheric layers before leaving the world behind. Along the way, clouds, temperature, and molecules in the gas absorbed it in different ways. By the time the light reaches Webb, it carries traces of the regions it has traveled through. Webb's task is not to magnify SIMP 0136 until individual clouds come into view. Instead, the telescope reads the signatures hidden within the light and follows how they change as the object rotates. The first step is to separate the light into a spectrum. Infrared light from SIMP 0136 initially reaches the telescope as a blended signal. Webb's instruments divide that signal into many narrow wavelengths, somewhat like a prism separating white light into different colors. But instead of producing only a beautiful band of color, the spectrum also reveals places where the light becomes weaker or stronger. Each molecule in the atmosphere interacts with light in its own way. Methane absorbs strongly at certain wavelengths, carbon monoxide leaves signatures at others, and carbon dioxide has its own distinct absorption pattern. Clouds also alter the light, while temperature determines how much radiation is emitted from each atmospheric layer. A spectrum is therefore somewhat like a piece of music played by many instruments at once. When the entire orchestra performs, a listener cannot see each musician through the sound, yet can still recognize the piano, the violin, or the beat of the drums by their distinctive tones. The light from SIMP 0136 also contains many overlapping signatures. Scientists analyze them to identify which molecules are present and which atmospheric layers are contributing to the signal. A single spectrum describes the state of SIMP 0136 at only one moment. Webb does something even more important. It continues observing as the world rotates. SIMP 0136 completes one rotation in about 2.4 hours. During that time, different regions of the atmosphere turn toward the telescope one after another. If a warmer area comes into view, certain wavelengths brighten. When a region with thicker clouds passes across the visible side, light from deeper layers may weaken. Webb records these subtle changes continuously, creating a sequence of spectra over time. On the 23rd of July 2023, Webb's NIRSPEC instrument observed SIMP 0136 for more than 3 hours. This was long enough to cover more than one complete rotation. During the observation, NIRSPEC collected 5,726 spectra, averaging one new measurement about every 1.8 seconds. That large number does not mean the atmosphere changed completely every 2 seconds. Continuous measurements help Webb avoid missing the smallest variations, as an atmospheric region slowly rotates into view and then disappears again. Each measurement is like a single frame in a long film. One frame alone reveals very little, but when thousands are placed in sequence, motion begins to emerge. Later, the MIRI instrument observed SIMP 0136 at longer infrared wavelengths. Its measurements were separated by about 19.2 seconds, slower than NIRSPEC, but opening a different region of infrared light. NIRSPEC and MIRI were therefore not repeating the same task. They complemented one another, allowing scientists to read light from a wider range of atmospheric regions. This method can be compared with the way weather satellites follow a hurricane over the Atlantic Ocean. An ordinary visible light image shows the shape of the clouds. An infrared image highlights the temperature of the cloud tops. Another channel tracks water vapor in the air. No single layer of data tells the whole story, but when they are placed together, the structure of the storm becomes clearer. Webb cannot see SIMP 0136 as a broad map like a satellite image of Earth. Even so, different wavelengths still act like separate observing channels. Some bands carry information from the upper atmosphere, others emerge from deeper cloud regions, and certain bands are especially sensitive to specific molecules. The atmosphere of SIMP 0136 can be imagined as a tall building, with no solid floors separating one level from another. All the layers of gas blend together, but each altitude has its own pressure, temperature, and types of clouds. Some wavelengths carry information only from higher levels, like windows looking into the upper part of the building. Other wavelengths probe more deeply before the atmosphere blocks them. Shorter infrared wavelengths can carry information from deep regions where the pressure is high, and models suggest iron-bearing clouds may exist. Another group of wavelengths is more sensitive to the silicate cloud layer. Higher still are regions where temperature differences and magnetic activity leave clearer signatures. These windows do not open onto completely separate layers. Each wavelength usually receives light from a range of depths, and those ranges may overlap. Still, the differences are large enough to show that the atmospheric layers do not all change in the same way. When one region of SIMP 0136 rotates into view, light from the deeper atmosphere may increase while the signal from higher layers remains almost unchanged. At another time, wavelengths sensitive to upper atmospheric temperatures may vary more strongly, while light from deeper clouds changes very little. If the entire atmosphere behaved as a single layer, the light curves at every wavelength would look nearly alike. They would rise together, fall together, and reach their peaks at almost the same time. Instead, Webb recorded many light curves with different rhythms. Some peak earlier, some brighten more slowly, and some move in nearly opposite directions. These differences are evidence that the atmosphere has depth. The upper and lower layers are not perfectly synchronized. A warmer region high above may not lie directly over a thinner cloud opening below. Atmospheric currents at different altitudes may also move at slightly different speeds, gradually shifting features out of alignment. A more familiar example can be found during a changing day of weather over the Great Plains of the United States. Low clouds may drift in one direction, while higher cloud bands are carried elsewhere by stronger winds. Temperature near the ground, humidity in the middle atmosphere, and air currents at higher altitudes do not necessarily reach their maximum values in the same place. To the eye, it may all appear to be a single sky, but meteorological instruments reveal many layers of motion within it. SIMP 0136 has its own moving layers, except that no weather station, aircraft, or satellite can pass through them. Every piece of information must be extracted from the light-reaching Webb. Scientists begin with the real data, how much the brightness changes at each wavelength and when those changes occur. They then construct computer models of the atmosphere. Each model tests a different arrangement of temperature, clouds, and chemical composition. One model may place a thicker silicate cloud layer in one region. Another may test a warmer area in the upper atmosphere. A different model may adjust the amounts of methane, carbon monoxide, or carbon dioxide. The computer calculates how light would escape in each case, then compares the result with the spectra Webb actually collected. When a model does not fit, its simulated light curves differ from the real data. They may peak at the wrong time, vary too strongly, or fail to reproduce the correct absorption signatures. Better-fitting models reproduce several features at once, from the overall shape of the spectrum to the way each wavelength changes throughout the rotation. This process is not simply a matter of imagining a picture and forcing the data to match it. Every explanation must pass many tests. A model that explains one wavelength but fails across the others is not convincing enough. A stronger model must simultaneously account for the temperature, clouds, chemistry, and pattern of change over time. From this process, scientists build an indirect map of the atmosphere. This map does not show the sharp outlines of individual clouds, nor does it identify the exact longitude of every warm region. Instead, it indicates where certain areas may be brighter, which atmospheric layers are changing the most, and which processes are most likely producing the observed signal. It can be compared to standing outside a house at night with all the curtains drawn. A person outside cannot see the rooms within, but the light leaking through can still reveal certain things. A warm, bright window may suggest that a lamp is on inside. A darker area may be covered by a heavier curtain. If the color of the light changes, the source behind it may have changed as well. For SIMP 0136, the curtain is its hot, dense atmosphere. Webb does not see through it in the ordinary sense, but it measures how much light escapes at each wavelength. As the world rotates, different parts of that curtain pass through view, revealing a sequence of changes that scientists can analyze. Thousands of spectra therefore become more than a collection of numbers. Together, they create a film made of light, in which every moment shows how the atmosphere is releasing energy. When that film is separated into many wavelengths, the atmospheric layers begin to reveal their own individual rhythms. The deeper atmosphere may reveal changes associated with iron clouds. The middle region carries the signatures of silicate clouds. Higher layers reflect temperature differences and may be influenced by auroral activity. Certain spectral bands also vary in ways suggesting that carbon-bearing molecules are not distributed exactly the same across every region. Webb has not given us a complete image of SIMP 0136. We still cannot see an individual storm, count its cloud bands, or determine the precise shape of a warmer region. Illustrations of the object therefore remain artistic interpretations guided by scientific data. What Webb provides is a different way of observing. Instead of seeing the weather directly, the telescope follows the effects that weather leaves behind in the light. Clouds alter the amount of heat that escapes. Temperature makes certain wavelengths brighter. Molecules absorb specific parts of the spectrum. Rotation brings each atmospheric region into view in turn. When all these signatures are combined, a point of light begins to acquire depth, motion, and a history of change over time. It is no longer merely an infrared dot in the data, but a world with layered clouds, warmer and cooler regions, and chemistry that is always in motion. This method is especially important because most worlds beyond our solar system are also too distant to appear as clearly defined spheres. Many exoplanets are known only through tiny amounts of light, often overwhelmed by the brightness of their host stars. If scientists hope to study weather on those worlds, they must also learn to read the subtle changes hidden within their spectra. SIMP 0136 is easier to study because there is no bright star beside it. The light Webb collects comes directly from the object, allowing its atmospheric signals to stand out more clearly. It acts as a natural training ground where indirect mapping techniques can be tested before they are applied to planets that are far more difficult to observe. Using NIRSPEC's 5,726 spectra and MIRI's sequence of measurements at longer wavelengths, scientists have transformed a single point of light into a layered picture. That picture is still missing many details and will continue to change as more data become available, but it shows that we do not need to see a cloud directly to know that weather is taking place. As long as the light is stable enough to measure, the rotation is clear enough to follow, and the instruments are sensitive enough to separate individual wavelengths, a world 20 light-years away can gradually reveal its atmosphere. SIMP 0136 is therefore more than a strange object drifting among the stars. It is also teaching scientists how to listen to weather through light, preparing them to observe exoplanets that orbit close to bright host stars and are far more difficult to see. What the James Webb Space Telescope has discovered about SIMP 0136 does more than help us understand an object drifting freely about 20 light-years from Earth. This world is also opening a new way to approach many more distant gas giants whose atmospheres remain hidden within the glare of their host stars. Most known exoplanets orbit a star. From Earth, the planet and star often appear so close together in the sky that their light nearly blends into a single point. While the star produces an enormous amount of energy of its own, the nearby planet reflects only a fraction of that light, or emits a far weaker amount of heat. The difference in brightness can reach millions or even billions of times. Finding the planet's light is therefore much like trying to see a firefly flying beside a stadium floodlight. The firefly is still there, but the much brighter source has almost completely hidden its signal. Telescopes can use several techniques to suppress the star's light, but the remaining signal from the planet is still extremely faint. Even a small amount of starlight leaking through the instrument, or a slight change in the telescope's stability, can make atmospheric measurements difficult. To determine what kinds of clouds a planet has, how its temperature varies, or which molecules are present, scientists must separate a very faint signature from a source that is vastly brighter. SIMP 0136 does not present that obstacle. It has no brilliant host star beside it, so the infrared light collected by Webb comes mainly from the object itself. The telescope does not need to block out a star before it can begin reading the atmosphere. Subtle changes in brightness, therefore, stand out more clearly and can be followed continuously through each rotation. SIMP 0136 is also relatively nearby on the scale of the Milky Way. 20 light-years is still far beyond the reach of present-day human travel, but in astronomy, it lies within the solar system's neighborhood. Light from worlds hundreds or thousands of light-years away becomes much fainter before reaching a telescope, while SIMP 0136 is close enough for Webb to collect thousands of spectra during a single observation. The object itself also shines clearly in infrared light because it is still young and hot. It has not yet lost all the heat left over from its formation, so its atmosphere continuously radiates energy that Webb can measure. Its rotation period of only about 2.4 hours also allows astronomers to observe nearly every longitude within a short span of time. This combination makes SIMP 0136 an especially favorable target. It is close enough, bright enough in the infrared, fast enough in its rotation, and free from the glare of a host star. During a single night of observation, scientists can watch different atmospheric regions rotate into view, compare light emerging from different depths, and detect changes in the weather between one rotation and the next. In this sense, SIMP 0136 resembles a natural laboratory without walls, a roof, or instruments arranged by human hands. Atmospheric processes unfold naturally in the darkness between the stars, while telescopes observe from afar and read the traces those processes leave in the light. This laboratory allows scientists to test an important question. When we observe a planet from a great distance, is a single measurement enough to describe the entire world? The data from SIMP 0136 suggests that the answer is often no. If Webb observed the object for only a few minutes, it might happen to catch a warmer atmospheric region facing Earth. The spectrum at that moment would carry the signature of a higher temperature and might lead us to think the entire world resembled that region. An hour later, the warm area would have rotated out of view, a thicker cloud layer might have appeared, and the light would tell a slightly different story. Both measurements would be accurate, but each would describe only one state at one moment. The difference would not necessarily come from an instrumental error. It might simply mean that the weather had changed, or that another region of the world had rotated into view. The same would happen if Earth were observed from far away. A measurement taken while the Pacific Ocean faced the telescope would differ from one taken when North America, the Sahara Desert, or a large storm system came into view. None of those measurements would be entirely wrong, but each would represent only one part of the planet. For distant exoplanets, this difference can easily be overlooked. Many targets are observed for only a short time because telescope time is always limited. From a single spectrum, scientists attempt to infer the temperature, chemical composition, and cloud structure of an entire world. SIMP 0136 reminds us that those results may sometimes reflect only the region facing us at the moment of observation. Chemical composition can also change with rotation. A rising region of hot gas from the deep atmosphere may carry more carbon monoxide. Another area may have conditions more favorable for methane, or may make the signature of carbon dioxide appear more clearly. As these regions rotate into view one after another, the spectrum of the same object changes. This means that a planet does not necessarily have one atmospheric formula that applies everywhere. Numbers describing the amounts of methane, carbon monoxide, or carbon dioxide are often averages or the best-fitting values for the particular moment of observation. Beneath those numbers may lie an atmosphere divided into many regions and layers, constantly mixing itself. SIMP 0136 also shows that clouds are not the only possible explanation for every variation in brightness. In the past, when a world brightened and dimmed, the natural explanation was often that regions of thicker and thinner cloud were rotating through view. Webb has shown that temperature, atmospheric currents, chemical composition, and magnetic activity can produce similar signals. This lesson is especially important when studying directly imaged gas giant exoplanets. A brighter region is not necessarily a gap in the clouds. It may be a hot spot in the upper atmosphere. A darker area does not necessarily contain more cloud, but may simply be cooler or may absorb light more strongly because of a particular molecule. To distinguish among these possibilities, telescopes must observe at many wavelengths and follow the object for long enough. Only by seeing how the light curves change over time can scientists separate the effects of clouds from those of temperature and chemistry. The magnetic activity of SIMP 0136 raises another question. On gas giant exoplanets, magnetic fields may do more than protect the atmosphere or produce radio signals. They may also deliver energy into the upper layers, changing the temperature and influencing chemical reactions. If a researcher used a model that included only internal heat and light from the host star, an atmospheric region heated by auroral activity could be difficult to explain. The data from SIMP 0136 suggests that magnetic activity should be treated as a genuine part of weather on giant gaseous worlds, rather than as a phenomenon occurring outside the atmosphere. The atmospheric layers may also move without remaining perfectly synchronized. Deep clouds may be carried by winds at a different speed from warmer regions above them. A structure appearing at one position during the first rotation may no longer be in exactly the same place during the next. When one wavelength reaches its maximum before another, that phase difference may reveal that atmospheric layers are sliding past one another. On more distant planets, similar signatures might be dismissed as noise if scientists did not know that an atmosphere can move according to several different rhythms. SIMP 0136 provides a clearer case for testing models and examining how the light changes when different atmospheric layers do not move together. These lessons will become useful as future telescopes begin directly imaging more gas giant planets. Some young worlds remain hot after formation and shine clearly in infrared light. They may orbit farther from their host stars, making their light easier to separate than that of planets in closer orbits. When a new point of light is discovered beside a star, scientists will not only ask which molecules it contains, they will also want to know how quickly it rotates, whether its spectrum changes over time, how its cloud layers move, and whether its magnetic field is heating the upper atmosphere. SIMP 0136 is helping prepare us for those questions. Because its light is easier to observe, these methods can first be tested under more favorable conditions. If a model cannot explain the data from SIMP 0136, it is unlikely to be reliable when applied to a fainter exoplanet lying beside a bright star. From this isolated world, scientists can learn how to distinguish a thick cloud layer from a region of cooler gas, how to recognize chemistry changing with rotation, and how to combine infrared data with radio observations. Every technique refined here will become another tool for reading worlds that are far more difficult to see. Its isolation once made SIMP 0136 difficult to classify, yet that same isolation is what makes it so valuable. With no host star nearby, the faint light from its atmosphere does not have to compete with a source millions of times brighter. This world drifts alone, and because of that, its voice in the infrared becomes easier to hear. Through SIMP 0136, something else has gradually become clear. Studying atmospheres beyond the solar system is not simply a matter of identifying a list of molecules. A world is not a motionless sample of gas sitting inside a laboratory. It rotates. Its atmospheric layers move, clouds form and disappear. Warmer and cooler regions develop, and sometimes a magnetic field adds even more energy to the upper atmosphere. To understand a planet, we must observe it long enough to recognize the rhythm of its changes. We must study many wavelengths to look into different depths, and we must accept that today's spectrum may differ slightly from tomorrow's, not because the instrument is wrong, but because the world itself has weather. After more than one complete rotation observed with NIRSPEC, followed by another sequence of measurements with MIRI, the James Webb Space Telescope brought its monitoring of SIMP 0136 to an end. The instrument stopped collecting data, while the recorded signals began their journey through analysis here on Earth. But 20 light-years away, there was no moment marking the end of the observation. SIMP 0136 continued to rotate. Its mineral cloud layers kept moving. Heat from the interior continued to rise, and different atmospheric regions continued to appear and disappear from our line of sight. The world has no awareness that its light has just been separated into thousands of spectra, or that subtle changes within its atmosphere are helping humanity learn how to read the weather on distant planets. It simply continues its solitary journey through the Milky Way, carrying an atmosphere that never stops moving. And even after Webb's observation has ended, the story of SIMP 0136 continues, because on this world without a sunrise, the weather is still unfolding. After the James Webb Space Telescope ended its hours of observation, SIMP 0136 continued rotating through the emptiness, 20 light-years from Earth. A warmer region of the atmosphere slowly moved out of view, causing the infrared brightness at certain wavelengths to fade while signals from deeper layers gradually became more distinct. Nearly 2.5 hours later, the original region returned, but the atmosphere may already have changed slightly. A cloud layer may have grown thicker, a current of hot gas may have shifted to a different position, and the chemical composition of that region may no longer have been exactly the same as before. On Earth, people often experience time through light. Morning begins when the sun appears, the afternoon passes as the color of daylight slowly changes, and the day ends beneath a darkening sky. SIMP 0136 has no such markers because it does not orbit a host star that could create the familiar cycle of light and darkness. Even so, time there is still measured by a rotation lasting only about 2.4 hours, by heat slowly rising from within, and by atmospheric currents continuously carrying matter through different layers. All of these motions eventually leave traces in the light. When a warmer region turns toward the telescope, the infrared brightness increases slightly. As that region disappears from view, the signal fades and other atmospheric layers begin to stand out more clearly. Some wavelengths reflect the influence of clouds, while others reveal changes in temperature or chemical composition. Through these tiny variations, an object that appears only as a point of light, barely, has gradually revealed a layered atmosphere that is deep below. There may be cloud layers containing iron. Higher up are silicate clouds formed from materials that, on Earth, are found in rocks and sand. Above them lie regions of gas shaped by temperature, convection, and perhaps magnetic activity as well. Webb has not directly seen individual clouds or a complete storm, but the changing sequence of light shows that the atmospheric layers are neither uniform nor moving in the same rhythm. Even with the growing amount of data, the origin of SIMP 0136 remains uncertain. It may have formed directly from a cloud of gas, in a process closer to the birth of a brown dwarf, or it may once have belonged to a planetary system before gravitational interactions cast it out. Both possibilities are consistent with an object now drifting freely through space, while the remaining evidence is not yet enough to determine which path truly occurred. Auroral activity also remains an unfinished part of the story. The strong magnetic field and radio signals suggest that charged particles may be carrying energy into the upper atmosphere. But the source of those particles is still unclear. They may be accelerated by the rotation and magnetic field of SIMP 0136 itself, or they may come from interactions with an undiscovered moon. For now, the possibility of a satellite remains only a hypothesis, but it suggests that much about this world is still hidden behind the signals our telescopes can detect. The cloud layers may not remain stable for long periods either. Some structures could change after only a few rotations, while larger regions may persist longer before slowly being reshaped by atmospheric currents. The chemical differences detected by Webb may represent stable regions, or they may be temporary states created as hot gas continually rises from deeper layers. There is no need to resolve every one of these questions immediately. What matters more is the way SIMP 0136 expands our idea of what a world with weather can be. An atmosphere does not need light from a nearby sun to remain active. Inside an object large enough, Heat left over from formation can survive for hundreds of millions of years, slowly escaping and sustaining currents of gas that never stop changing. Weather there does not begin with water as it does on Earth. Under far hotter conditions, the materials that make up rocks and metals can condense into clouds, drift through the atmosphere, and evaporate again as they sink into deeper, warmer regions. Even auroras may form in a different way, without depending entirely on the wind of a nearby star, but instead involving a powerful magnetic field, rapid rotation, and streams of particles that are not yet fully understood. SIMP 0136 shows that weather requires only a source of energy, enough matter, continuous motion, and time for change to develop. On this world, the energy lies within its still hot interior. The matter fills its enormous atmosphere. The motion comes from rotation, convection, and magnetism, and time continues to pass in cycles of 2.4 hours, even without a sunrise to mark them. While the light from SIMP 0136 was crossing 20 light-years of space on its way to Webb, the world completed countless additional rotations. The atmospheric regions once observed may have changed long ago. A cloud layer may have disappeared, a new warm region may have formed, and the currents of gas may still be carrying matter between the deep and upper atmosphere. What we receive is only the light of a moment that has already passed. Yet within that light are enough traces to show that SIMP 0136 has never truly been still. In the darkness of the Milky Way, it continues to rotate. Heat continues to escape slowly from within, cloud layers continue to shift, and different atmospheric regions continue to appear and disappear from view. No morning waits ahead, yet the weather on SIMP 0136 continues in a rhythm of its own, persistent and quiet in the darkness of space.